Hi there, this is nuclear physics. This one's lesson 11 and this one's nuclear radius. So there's two parts to this one, and this one we're going to cover the distance to closest approach and electron diffraction. So nuclear radius from alpha scattering. So I've actually done this in a question in the electric fields playlist, but you might not have seen that one. So I'm going to cover it again here. So what you can do is you can get an alpha particle, fire it at a sheet of gold, really thin gold, and the kinetic energy of the alpha particle will convert into electrostatic potential energy as it approaches the nucleus, stop, and then recoil back in the direction from which it came. Right, there's a couple of numbers here. You should probably write these down. Although this number at the bottom, it says 10 to the minus 14. It's actually 1 to 10 femtometers. Sorry if that's not very neat. Femtometers is to the power minus 15. Okay. Radius of an atom is approximately, that's correct, to the power minus 10 meters. You need to know them. Right, so what I'll do now is the same thing that I did in the electric fields lesson and take you through this. If you know how to do this, obviously have a go at it, but I'm going to go through it as an example anyway. So we've got the kinetic energy of the alpha particle, which is 7.68 MeV. We've got the proton number, Z number, of the gold nucleus. And what we need to do is attempt to find the nuclear radius, or what's actually the upper limit of the nuclear radius, distance closest approach. So the way to do that, it's quite tricky. So there's going to be work done, and work done is force times distance. But what I'm going to use for distance is R. Okay. So the work done is the conversion of the alpha particle's kinetic energy, the 7.68 MeV, into potential energy as it closes in on the nucleus. So the force that it's overcoming is the electrostatic repulsion from the nucleus. So if you remember, the force is Q1, Q2, divided by 4 pi epsilon naught R squared. And what we're going to do is sub that in for work done. So work done would be that force, Q1, Q2 divided by 4 pi epsilon naught R squared. And then obviously we've got to multiply by R. So the R's cancel and we're left with this expression here. And then all we need to do is rearrange for R. So R would be charge 1 times charge 2 divided by 4 pi epsilon naught multiplied by the work done, which we could call energy of the alpha particle. Right, so there's still a bit to do. So we've got charge 1, which is the gold nucleus, so that's 79 times the charge of a proton. So what's charge 2? Well, we know that alpha particles are a helium nucleus. So alpha particles have got 2 protons. So let's do that one here. So the radius or distance closest approach would be charge 1, which is 79 times E. E being the charge of a proton. 1.6 times 10 to minus 19 coulombs multiplied by 2 protons times E divided by 4 pi epsilon naught. Epsilon naught's a constant on the data sheet. 8.85 times 10 to minus 12. And then we need to find the energy of the alpha particle. So we need to convert the 7.68 MeV into joules. Do that in a different colour. So 7.68 mega, so times 10 to the 6 electron volts, and multiply that by 1.6 to the power minus 19, and that'll give us the energy of the alpha particle. So if you put that in your calculator, you'll get 1.2288, so I'll just say 9 times 10 to the minus 12 joules, and then you just need to put all your numbers in. So I'll do that here. So 79 multiplied by 1.6 to the minus 19 multiplied by 2. You could just square that because we're going to times it by it again. That's how I write it like that. then divided by 4 pi 8.85 times 10 to the minus 12, and then multiplied by the energy of the alpha particle. 1.229 times 10 to the minus 12. So it's a bit lengthy. That gives us 2.96 times 10 to the minus 14 meters. And if you want to turn that into femtometers, you can divide that value by 1 times 10 to the minus 15. So that's the answer, obviously. I'm just going to do the conversion now as well. So if you divide that by 1 point, I don't know why I've put point, 1 times 10 to the minus 15, that will give you 29.6 femtometers. Okay? So you need that technique. That's a common one that comes up. All right. So what I'm going to do now is give you a load of different example questions to do. It's the same technique, the same equation. You just need to use different numbers. All right. So here we go. So as you can see, I'm asking for the closest approach in femtometers or the energy in MeV. So this might take quite a while. The equation there is the equation that we've just used. I've got Z in as proton number and then E squared. Okay. And the 2 there, if you're wondering what that is, that's the number of protons in an alpha particle. And we're always using an alpha particle, so I've just put that charge in there. So 2 times Z is the proton number of whatever material that you're looking at. E is the charge of an electron. E alpha is the energy of the alpha particle. And to get the number of protons, you will, for the aluminium, iron, gold, uranium, you will need a periodic table. So you can grab one of them online. Right, so what I'll do is just give the answers for each one. So aluminium should have got around 5 femtometers. Iron's around 16.2 femtometers. Then working the other way, finding the alpha particle energy. Gold, you should have got about 4.8 MeV. Uranium, nearly 5 MeV. And this one, to calculate the nuclide, what nuclide it is, you would need to figure out the number of protons. And then once you've got the number of protons, you can look at the periodic table and then deduce the nuclide that's responsible. So if you did that correct, you would have got plutonium. All right, well done. So typical alpha energies are 5 to 8 MeV. Rutherford, obviously, when they did this, early 1900s, didn't have a particle accelerator. So can't we just keep accelerating particles to higher energies? Well, no, because as they approach higher and higher energies, alpha particles start to be absorbed. I believe Rutherford could only get up to about 8 MeV. So that was off the table anyway. So the formula above only tells us an upper limit of nuclear size. The closest approach is not the nuclear radius. Right, so we'll have to come up with a better method. So we need particles that don't experience a strong nuclear force. Now, from your particle physics, you should know that will be leptons. Leptons are not subject to the strong nuclear force, specifically electrons. So electrons are waves and nuclei are regularly spaced. So what effect can we take advantage of? So you've got spacers, you've got electrons behaving as waves. So we're going to take advantage of diffraction. And to get maximum diffraction, so you should know this from doing optics, the Young slit experiment. So to get maximum diffraction, what property of electrons must we fine tune? And it's that the wavelength must be similar to that of the diffracting object. Okay. So when we do that, we get a pattern like this in the bottom right, and that's called Fraunhofer diffraction. And we can use it to calculate the nuclear radius. All right, let's have a look at some explanation then. So when a beam of high energy electrons is directed at a thin solid, sample of an element, the incident electrons are diffracted by the nuclei of the atoms in the foil, which makes sense. The space between the atoms and the electrons will be diffracted. So the beam, the electron beam that we use, is produced by accelerating electrons through a potential difference of the order of 100 million volts. So we'll do a question in a bit where we have a beam of electrons and they've got an energy of 200 MeV, so 200 mega electron volts. So the reason that this works, the electrons are diffracted by the nuclei because the de Broglie wavelength of such high energy electrons is approximately the same size as the diameter of the nucleus. So in terms of femtometers, they're approximately the same. So you get really good diffraction that you can measure using a detector. So this diagram at the bottom might be making more sense now. So this is the equivalent of the diffraction grating experiment. So diffraction grating experiment, you use light. And in this instance, we just use a beam of high energy electron beam instead. So we use a detector to measure the number of electrons per second diffracted through different angles. And what you'll find on this graph, the detector reading drops and then starts to come up slightly. And where it drops, that's called theta minimum. So I'll give you an equation in a moment, and if you use that equation with that angle, you will get the nuclear radius. So the measurements show on that graph that as the angle of the detector from the zero order, so n equals 0, which is obviously the straight line if it wasn't deflected at all, the number of electrons, or the per second, the intensity, it decreases and then increases slightly. So decreases, increases, and then starts to come down again as you go towards n equals 2. So it's this n equals 1, the theta min, that we're interested in. So the scattering of the beam electrons by the nuclei occurs due to their charge. So it's the same as alpha scattering by a nuclei, except the electrons are attracted, not repelled by the nuclei. So just to reiterate, the angle of the first minimum from the center is measured and used to calculate the diameter of the nucleus. We must know the wavelength of the incident electrons. All right, so we're going to look at an example. So you might be wondering, how do we get the wavelength of electrons? So it's a little bit more complicated than what you get at A-level, but if you ever get this type of question, that equation will be given to you. The sine theta equals 1.22 lambda over 2r. So theta is the angle to the first minimum, which is what we're interested in. R is the nuclear radius, so you rearrange that to get r. We are going to use the energy of a photon, so energy is hc over lambda, to find the wavelength from the energy. It's not entirely correct, but it works quite well. So for this example, as you'll see, we can get the wavelength using hc over E. So h being Planck's constant, multiplied by the speed of light, and then the energy, we need to convert that into joules. So 200 mega electron volts is 200 times 10 to the 6. Multiply that by 1.6 to minus 19, that will convert the energy into joules, and that gives us 6.215 times 10 to minus 15 meters. Then we can calculate the nuclear radius, so we've rearranged that equation. So we take the r up, take the sine theta down. So 1.22 multiplied by the wavelength. Now the wavelength is the wavelength of the electrons. So that wavelength is the wavelength of the incoming electrons. And you see that gives us approximately 7 femtometers, which is very different to the 30 femtometers estimated from Rutherford scattering. Now, if you go on Google and look at, you type in on Google, you get the AI overview. The nuclear radius of a gold atom is approximately 7 femtometers. So even though we've technically used the wrong equation, it still works very well. Right, so what I want to do is finish with another question, which will be this one. So if you're going to pause and do this. So we're going to use sine theta is equal to 1.22 lambda divided by 2r. What we need, obviously, is the wavelength of the incoming electrons. So these ones have got an astonishingly big 420 MeV. We've got the angle, so we'll find the energy and then we'll calculate the radius. So we need to convert that 420 MeV. So 420 times 10 to the 6 multiplied by 1.6 to the power minus 19. That'll give us the energy in joules, which is 6.72 times 10 to the minus 11 joules. Then what we're going to use is the equation that we shouldn't really be using but works anyway. So energy is hc over lambda. I'm going to rearrange to get the wavelength of the electrons. So hc divided by the energy, which we just calculated. So 6.63 times 10 to the minus 34. Speed of light 3 times 10 to the 8. Divided by the energy, 6.72 times 10 to the minus 11. So that gives us a wavelength for the electrons. Now remember, these have got to be approximately equal to the actual wavelength. Actual diameter of the oxygen nuclei, which we'll soon find out if that's true. 2.9598 times 10 to the minus 15 meters. So that's the wavelength for the electrons. Then what we can do is use this equation, and we're going to calculate R. So I'm going to do I'm going to write this a bit different. So sine theta. So 1.22 divided by 2 is 0.61. So 0.61 times the wavelength divided by R. So R would give us, I just realised I didn't change my colour back. Not that it really matters. So 0.61 times the wavelength of the electrons. So 2.9598 times 10 to the minus 15 divided by sine 44. So that gives us 2.6 to the minus 15. And just out of interest, Google tells us that the radius of an oxygen nuclei is allegedly, because I've never measured it myself, 2.8 to the minus 15 meters. So pretty close. Right, hope you found that all right. And yeah, good luck.